Okay, hi everybody. So now I'm going to, in this video, I'm going to explain in the chapter 3, which is about the vibration of diatomic molecules. So basically, we'll be looking at the spectra or the spectrum of pure vibration. Now, there is a large part, if you want, of this slides of this chapter that we can easily skip because it's nice to know, but it's not actually very important to our spectroscopic treatment. So basically, we will answer the same sort of questions as we did for the rotation of molecules. So how could we observe that a molecule has a vibrational motion? Obviously, the same question, is classical mechanics enough? The answer is no. And yes, we need to introduce quantum mechanics, but we will see very interesting physics going on actually when we talk about vibrations of molecules. Now, it's interesting to know that the diatomic molecules absorb electromagnetic radiations. And as you know, the electromagnetic spectra goes, we have the visible range between 400 and 750 nanometers approximately, but then we have the infrared and the ultraviolet. Basically, the electromagnetic radiation absorbed by diatomic molecules are in the infrared region of the spectrum. So the wavelength is between 2 and 100 microns. And the near infrared, which is a bit smaller. Okay, so basically the molecules absorb in the infrared. If you want, infrared is related to temperature, right? The reason I'm saying that you see that night vision, for example, or if you have a camera that looks in the infrared, so basically it looks at the temperature of the bodies that are moving. So when we say that molecules absorb electromagnetic radiations in the infrared, it probably means that, if you want, we can say it like that: when we heat or vibration of molecules is related to temperature, right? So as you remember, when we talked about at the very first chapter, we talked about the black body radiations. Well, we were heating the black body and then it was emitting light or absorbing it, basically. Same thing, because it's a black body. And that was explained by the vibration of dipoles. So heat results in vibrating molecules. So voilà. When you feel hot, your body molecules or your skin molecules are vibrating more. That's it. Great. Now, as we did before, I will just say something about experimental observations. So that's the diatomic molecule, the HCl. Don't look into the equations. I don't care about them. They're not really fundamental here. The fundamental point is that we could observe in the absorption spectra, if you want, that we have one big intensity peak or band, we can call it, and then we have smaller ones kind of nicely distributed around it. So this reminds us, this shape, for those who know Fourier transform, for example, it reminds us of Fourier transform. So it's as if we have a fundamental line and then we have the so-called harmonics, right? And this is actually what's going on in here. But this is experimental, and now we need to treat, theoretically speaking, the vibration of a diatomic molecule, and then see actually if our explanations or our models do explain this experimental vibration. So obviously, before doing it, we will know at the very beginning that classical mechanics won't do it. So this sort of spectra, just to say as a general information, chemists are more used to this sort of spectra and they know how to analyze it. But this is for large molecules, okay? Now, obviously, our work is just for diatomic molecules, the vibration of diatomic molecules, the infrared spectroscopy, if you want. which will be less complicated than this shape of spectra, obviously, but it's the building block for it. Great. Now, as I said, I won't go into the details of the simple classical treatment because it's very redundant and it will not help us in. So you can read the slides. There will be a large number of slides that you can read for your own sake, for your own information. But that's I will give you, if you want, the conclusion of them. Basically, when we have a vibrating mass, okay, the simplest approximation that we know is the harmonic approximation, which means that a mass that is vibrating around an equilibrium position as if it's bonded or linked with a spring. And this is the physical motion of it around the equilibrium position. There is a restoring force. We can either look into the elongation of the spring with regard to the equilibrium position as being the zero of our coordinates, or actually we can look into the elongation considering that the side of the extremity of the spring is being the zeros, and then it's the same thing, but just the expressions differ. Now this here shows the potential variation. So you clearly see that when we are at the equilibrium position, there is no potential energy, and then on both sides of the vibrating motion of a mass, well, the potential energy increases in a parabolic way. And this is very clearly and very easily the harmonic oscillator, the potential of a harmonic oscillator. Well, here it just states what I just said. Okay, so there is a force, a restoring force, which is related to the spring constant of the spring, and x is the displacement, and then from that we can derive the potential because the force is deriving from the potential, and we can get the shape of the potential, which is parabolic. You can just read that, but I can tell you it's general information. We do not have the luxury now to go to such form of general information, although you know it, but read it if you wish. Great. Now this is the other way to look at things. So instead of putting x, well, it's L minus L0. It's the same thing. We just change the reference point. Now, there's several ways to find the solutions. Our goal at the end is to find the frequency at which this mass is vibrating. Well, no strings attached. All calculations are nice, but, well, it's a normal second order differential equation that leads to the very known expression of the vibrational how it's called, frequency, which is half, or if you want, omega. So it's half radical k over m, k being the spring constant of the spring, m is the mass, and the frequency of it will clearly depend on the mass and the spring constant. So that's the frequency of a vibrating mass related to a spring. Well, things get similar if we have a system of two masses instead of one mass. Well, the reference point will be the center of gravity, and then we can look into the elongations of one mass and the other, and the total elongation would be the sum of it. Well, I won't go to these details. What interests me is that, look, now, as we did in the rotational energy, basically we know now that if we have a two-body problem, two masses, two atoms, we can assimilate that into one body problem that has the reduced mass that you know now, m1, m2 over m1 plus m2. Okay? R here is going to be somehow the interatomic distance of the system, which is the distance between the two masses. Okay? And then we can look into the vibration from this point of view. Obviously, the same mechanical treatment will give us that the vibration of, and I think in the first formula I have missed the 2 pi, because that's 2 pi f, omega equal 2 pi f, so that's omega and that's 2 pi f. Omega is radical k over m. Now, for a molecule formed by two masses, m1 and m2, in which the reduced mass is mu, then this system will be vibrating at a frequency nu equal 1 over 2 pi radical k over mu. That's the message that I want you to get from the classical treatment. Now, obviously, you can see that this frequency of vibration can take any value, continuous values, as m get increased or as k get increased or reduced. There is no quantification in that. And obviously, classical mechanics won't be able to explain this way what we see on the experimental side of the spectrum. Okay? Well, again, this is the potential, which is the harmonic potential, classical harmonic potential. Great. Now, similar conclusions as before. All elongations of the spring are possible, so no specific values for the energies. So it's a continuous phenomenon, right? So the frequency can increase or get reduced in a continuous way. There is no quantification factor in the expression that we just seen, which means that if vibration happens because of absorption or because of emission, or vibration will cause emission, well, it means that we can emit in an indefinite way or absorb in an indefinite way. And that's exactly the famous UV catastrophe that we talked about in the first chapter, right? So this is obviously not true, and this could not explain the black body radiations. So we needed the quantum mechanics from Max Planck concept. Okay. How to do that? Well, again, the potential between two molecules that are vibrating is called the Morse potential. Okay. You are not responsible neither for this information. Okay. So what will interest us is this. What you look in here, you're looking at the potential energy, so the interaction, the potential of the interaction between two atoms, separate by a distance r. And RE here is the equilibrium distance between them. So it's, if the system is vibrating, then it goes around this equilibrium distance, the two masses. Now, the harmonic approximation, the harmonic oscillator, gives us this parabolic shape of the potential. So it's a symmetrical one on either sides, which is not correct. And you will see why. The more real one is called the Morse potential, and this is the one in bold line in here, or in full line. Obviously, you see that when the distance gets higher and higher, so the two atoms are getting away the one from the other, the potential energy goes and then is going to get stuck into a point where after it there's no potential. And in fact, this is logical because I cannot stretch a molecule indefinitely. Okay, the harmonic oscillator here says that the more you go away, the more the potential is going to get higher and higher and higher. Well, that's not real, because this means I can stretch a molecule like 2 kilometers away, the two atoms, and still there's potential. But that's not true. After a certain stretching, the bond will break. So there is an energy after which the molecule is going to dissociate, to break. Okay? Great. And when the molecules get closer, or the atoms get closer the one to the other, the potential energy increases drastically, or in a more rapid way, because there is a very close potential called the Morse potential here, basically. It depends on r over 6, or 1 over r to the power 6. Now, the way, if you want to look at it, if you want to remember all that, imagine the two atoms as two people in the phase of their relationship. At the beginning, if you want, there is no interaction, almost no interaction, very weak interaction. They just see each other from classes. Now, the more they get together, closer and closer in the same class, there will be an attraction. there will be an attraction, they will start to love each other, etc. And at a certain point in equilibrium, they will get married. And once they get married, then the potential between them start to be repulsive. Repulsive, so either they die or they get divorced. And this is actually, this Morse curve is very nicely understood, at least in my brain, like this. So you can remember it like that, okay? Now, we've talked a lot. Let's just get into action. Now, the quantum mechanical treatment shows that if we put the potential, the harmonic potential, in the Schrödinger equation, then we will get into the energy of the molecule, the vibrating molecule, being quantified with a quantum number called V. So this is not nu, this is V for vibration. V plus half h over 2 pi, so h bar, radical k over mu. Radical k over mu is omega. Omega, which is the pulsation of the vibration. Great. Well, the allowed energies, as you know, they will be quantified clearly, like half for V equals 0, it's half hv, h nu, because this is omega over 2 pi, it's in nu. So this is V, and this is nu. Nu as frequency. So nu is the frequency, 1 over 2 pi radical k over m. So you know that, you know this relation between pulsation, omega, and frequency. Omega equal 2 pi f, or 2 pi nu, and that's here, okay? Because omega is radical k over mu. So it's V plus half h nu. That's the energy of each level. So for nu equals 0, so for V equals 0, the energy is half nu, h nu. It's 3 over 2 h nu, 5 over 2 h nu, okay? So the separation between the different energy levels allowed by quantum mechanical treatment, considering that the potential is harmonic oscillator, there are equal spacing between these energy levels. And this, as you'll see, it's going to be disturbing. Now what you see here is actually the psi, the wave function of the electron in quantum mechanical treatment. So it tells us the distribution, the psi squared, the distribution, the probability of electron presence in this well of harmonic oscillator potential. Okay, so again, making things practical, what we need to keep in mind, quantum mechanics quantifies the energy of vibration of a diatomic molecule. The quantum number is V. Nu is the frequency of this vibration, and the vibrational energies allowed in the case of harmonic oscillator, so the potential is an harmonic oscillator, then it's related by this, E equal V plus half h nu. Okay? Forget about that. Well, the first thing that we can see basically from the quantum mechanical treatment is that even for the lowest energy, vibrational energy level, so the lowest quantum number, V equals 0, there is energy of vibration. And that's what I said, I think, in one of the videos before, that the lowest vibrational state of a molecule is not 0, while the lowest rotational state of a molecule is 0, if you have seen that in the chapter before. Okay? Now, spectroscopically speaking, now here where we get to start, this is where we start to get interested for our work. All the things before are nice physics to know, but honestly, you are not responsible of them. I mean, as for like dealing with spectra, it's nice to understand the physics. Now, quantum mechanics gives us this quantification of the vibrational energy, EV. Nu being the frequency, and this is the quantification. Now, as we said before, the vibrational energy will be manifested by a form of electromagnetic radiation. And this is why, spectroscopically speaking, we introduce a wave number-like term, which we call the vibrational spectral term. And to do that, well, we will just introduce C up and down. So h nu, which is the vibration of electromagnetic radiation, so that's the energy, sorry, instead of h nu, we will say hc nu over c. So nu over c is nu bar, which is a wave number term. We call it G. Okay, so in rotation we called it f of j. It was f, the spectral term of the rotation. Now for the vibrational spectral term we call it G of v, obviously, because v is the quantum number vibration. Clearly you can see that GV is nu over c v plus half. How we get that? You just put, in fact, v plus half h nu equal hc gv. So h and h, they go away, c goes down, and then you have gv equal v plus half nu over c. Now nu over c is called omega e, which is the vibrational wave number. It's a name. We call it the vibrational wave number, nu over c. So that's frequency over c. It's the vibrational wave number omega e. So the spectral term that we will basically deal with all the time in the vibrational spectra is omega e v plus half. This is going to be the vibrational term, the spectral vibrational term for one given energy, for a given v. Okay? Now obviously, in spectra, we deal with transitions. So look, there is several rules that governs the interaction between a molecule and electromagnetic radiation. So a vibrating molecule cannot interact with electromagnetic radiation unless it's a dipole, unless there is a vibrating dipole moment. Okay? So which means that if we have a heteronuclear, so different nucleus or different nuclei, so two different atoms basically, we will have a dipole moment because the charge will not necessarily be the same. And well, then we can have vibrational absorption or emission. Okay? But the transition rules, which means the selection rules, which levels of vibration can go to which level of vibration if we vibrate, if we absorb light, or which level can go down to another level if we are to emit light, then it's delta V equal plus or minus 1. Obviously, plus 1 is when the molecule absorbs light. It moves from one level of energy, V, to the one just after it, so that delta V equal 1, and vice versa for the emission. Now look at the interesting thing here. For delta V equal plus 1, it's absorption, and delta V minus 1 is emission. Let's take the case of absorption, for example. Delta EV is going to be the difference of the energy levels. Obviously, it's E final minus E initial. Since it's absorption, so the final level is just 1 unit in V, so it's V plus 1 compared to the one before it, from which the vibrational energy has absorbed light. So we are moving from one level EV to the level just after it, which correspond to V plus 1. So delta EV is EV plus 1 minus EV. Now, you've seen what EV is. So you put V plus 1 here, and then you will see that if you make the difference, look, H nu, V plus 1 plus half minus V plus half. So this is the one that corresponds to EV, so it's H nu V plus half, and this is the one that corresponds to EV plus 1. Well, you notice that the difference is independent of V. It's always equal to H nu. It's interesting. This means whatever the transition is, either from 0 to 1, or from 1 to 2, or from 2 to 3, whatever, always the difference is going to be H nu. And this difference is the energy or the frequency that we will see on the spectra. Because what we see on the spectra comes from an emission or an absorption. Right? So, spectroscopically speaking, This is EV written in terms of the spectra, right? As a spectral term. Now let's take the case where we move from E corresponding to V equals 0 to E corresponding to V equal 1. Now, the wave number on the spectrum, as I said in the video before, is nothing else than the difference of energies, or difference in the spectral terms. So G in this case, GV 1 and GV 0. So when we do a transition, we get a line at a given wave number that we call nu bar spect. So that's on the spectrum. So on the spectrum, this nu bar spectrum comes from a transition between two levels, in this case in absorption from 0 to 1. Then we have EV over HC, because we are dealing with nu bar, so it's EV over HC, so that's the GV, that's the wave number, or the spectral term. And the same for 0. If you divide by HC, you will notice that, well, the spectrum, the wave number at which this transition will appear, will correspond to nu over C, which we just called omega E. Okay? Now this is going to be the same. If you calculate the same, if you go from 1 to 2, you will find that the spectra, the nu bar spectra, will also appear at nu over C. Now if you go to from 2 to 3, you calculate also the nu bar spectra, which is this delta G from between levels. It's also nu over C, or omega E. What does that mean? It means that, as I said, any transition by absorption, they will all coincide at the same spectral number on the spectrum. So we can't differentiate between them. So if I'm considering if the approximation, or if the potential was only the harmonic oscillator, as it's in the case in here, and as we have done to get this energy expression, well then I should, in any vibrational spectra, I should see only one peak. And God knows this peak comes from which energies transition. Maybe from all of them, maybe of one of them, I don't know. Because they all have this, they will all appear at the same spectral value, spectral wave number, which correspond to omega E. So clearly, the harmonic oscillator is not a good approximation. It's not a good approximation. Okay. Now what